So section 7.6 takes a different look at doing integration. Um, Essentially, they say, there's been a lot of really smart people doing integration for a lot of years, and they've written down stuff. And so why don't we just use what they've done? So there are these things called integration tables, where they're just a list of different integrals that people have already figured out. Now, I want to point out that in our textbook, I'm going to switch to the camera here. So in our calculus text here, um, on the very back here, we've got pages of integrals. Reference page 5. No, those are all derivatives. So reference page 6 to reference page 10 are all a bunch of integrals here. So they tell you, they say, hey, if you got something that looks like this, then it's going to end up looking like that. Um, I also have a whole nother book here that's got a bunch of things, but this is the Book of Standard Math, CRC Book of Standard Math Tables. Um, and from page, where does it start here? So from page 28, some elementary forms, on through, there's just a whole bunch of integrals, integral after integral after integral, and it goes all the way up to page 296. So, yeah, there's a lot of integrals that people have already figured out. Now, I claim that all the integrals in the table in the back of our textbook, you can actually figure out yourself using the techniques that we've learned. Okay. I think that perhaps in this book there may be a few others, but well, I'm not even sure of that. Anyway, let's do an example of how we might use a table here. So let's switch back to not on the camera. So I want to do the integral that's given here. Um, I look through the table and I look to see if I can find something that looks reasonably close to that. And I notice that the table's arranged in different ways. So on your reference page 6, it starts off with some basic forms. They then have some forms involving the square root of a squared plus u squared. The top of the next page, a squared minus u squared. The bottom of reference page 7 there is forms involving the square root of u squared minus a squared. And that's what I'm looking at here, is that they're talking about things that look like the square root of u squared minus a squared. And I'm saying, I think I got that, because I've got a 2y squared minus 3, and I want to say that that's equal to u squared minus a squared. So one thing I see is that a is equal to the square root of 3, and that 2y squared is equal to u squared. So u is equal to the square root of 2 times y. Likewise, du is square root of 2 dy. So I can make some substitutions to see if I can fit one of the forms. In fact, I already have one in mind, because I'm looking at number 42 this is on reference page 7 in the textbook. Number 42 has an integral of the square root of u squared minus a squared over u squared du is equal to something, and I'll write the something down in a little bit. But the point is, I'm thinking that this looks a lot like that. The numbers are a little different. This is a 1 and this is a 2. This is fine. A is just the square root of 3, but this has a 1 here and that's got a 2. So I've got to make this substitution where u equals square root of 2 times y. So let's see what happens when I do that. So taking this thing, I've got an integral of. So y then is u divided by the square root of 2. So I've got 2 times u divided by the square root of 2 squared, because I've got the y squared there, minus 3 all over y squared. But y is equal to u divided by the square root of 2. So I got u divided by the square root of 2 squared in the denominator. Then the dy becomes du divided by the square root of 2. Okay, too many square roots. So what I notice here, this is equal to that, this is equal to, when I take the square root of 2 and square it here in the denominator, that's going to be a 2, and that's going to cancel with that 2. So underneath the square root, it just becomes a u squared minus 3, which is looking a lot more like I wanted it here. Okay. The denominator here is now u squared over 2. I've got a times 1 over the square root of 2 times du. To divide by this fraction, I'm going to invert and multiply. So the 2 is going to end up on the top. So I got a 2 on the top. I got a square root of 2 on the bottom. I'll just pull those out in front. That's actually going to cancel to just be the square root of 2. But I'm left then with the square root of u squared minus 3 over u squared du. Okay. This now does look just like this one. So number 42, I'm going to write it all out now. Number 42 in this table says that the integral of the square root of u squared minus a squared over u squared du is equal to, where is it, number 42, minus the square root of u squared minus a squared over u minus the natural log of the absolute value of u plus the square root of u squared minus a squared plus a constant. Okay. Now, having a little experience in this, it looks to me like the way they did that was probably an integration by parts. Maybe. Actually, now that I say that, integration by parts, I probably would have just tried a trig substitution right away here. But anyway, so I'm looking at this saying, this is what the table is telling me. This is the thing I have. A is equal to the square root of 3 here. So what I end up with, 2 divided by the square root of 2 is the square root of 2. And then that's all times this stuff. So u squared minus a squared. So I've got minus the square root of u squared minus 3 over u minus the natural log of the absolute value of u plus the square root of u squared minus 3 plus a constant. Substituting back in, because I didn't start with u's, I started with x's. No, I started with y's actually. U is equal to radical 2 times y here. So this is radical 2 times negative. U was radical 2 times y, so when I square that, I'm going to have a 2y minus 3. U is equal to radical 2 times y minus the natural log of the absolute value of radical 2 times y plus the square root of 2y. Sorry, when I square the radical 2 times y, that should be a squared, shouldn't it? Yes, it should be minus 3 plus a constant. Looking up integrals is not necessarily straightforward. They're not alphabetical or anything like that. They're grouped by stuff they have in them. Do they have trig functions in them? Do they have radicals of quadratics underneath? Do they have radicals with linears underneath? All these different things that you might run across. You got to find those in the table and then find one that matches your integral, at least close, and then you got to do an appropriate u substitution to make it look exactly like what's in the table. Okay. Once you do that, then you can use that result to substitute your thing into, and then substitute back whatever you had to make u equal to make this fit. Substitute back to see what you end up with. Integration by looking it up in a trig table.